Hello again, everybody. Well done for completing lesson 2.1. This lesson, as we've seen, has been all about the sun. The sun is responsible for producing solar wind charged particles, and it's those charged particles, the solar wind, which ultimately generate the aurora on planet Earth. So to understand the aurora, we need an understanding of the sun. First of all, the composition and structure of the sun, which is what we've been focusing on in this lesson. The sun, as we saw, is made of plasma, ionized hydrogen atoms, mainly ionized hydrogen. Atomic hydrogen you could think of as looking a bit like this. This is the solar system model of an atom. It's not entirely accurate, it's very complicated, but we're not going to go into quantum mechanics here. There's no point for the purpose of this course and the purpose of this lesson. So for now it's safe to think as atomic hydrogen as looking a bit like this. The nucleus, the middle of the atom, consists of a positively charged proton, and in orbit, as you can see, there is a negatively charged electron. But the sun is so hot and so dense that the hydrogen gets ionized. The electron is stripped away from the atomic nucleus, the atom is broken up into its constituent parts. The sun, therefore, is composed mainly of plasma, positively charged protons and negatively charged electrons. Let's also have a look at the structure of the sun very quickly. Let's recap on what we've learned there. In the middle, in this picture, you can see that bright core. The core is where nuclear fusion occurs. Hydrogen, the lightest element in the periodic table, undergoes nuclear fusion. Under all of the heat and all of the pressure in the core of the sun, 16 million degrees Celsius, the hydrogen is fused into helium. Nuclear fusion kicks out an enormous amount of energy, and it's that outward pressure from fusion which in fact holds the sun up under its own crushing gravitational force. So the core is where nuclear fusion occurs. The next layer, if you like, is the radiative zone. This is where the energy from nuclear fusion bounces around through ionized hydrogen and ionized helium. So literally the energy from the core radiates through this zone, which is between 0.25 and 0.7 solar radii. So 25% to 70% the radius of the sun. After the radiative zone is the tachocline, which we'll look at a little bit later on. But first of all, we're going to look at the next layer, the convective zone. Now the convective zone is much cooler than the radiative zone, about 2 million degrees. And because of this, some of the heavier elements present in the sun, like carbon, like oxygen, can hold on to their electrons. And this means that this layer is opaque. It traps heat. So instead of heat just bouncing around like it does through the radiative zone, the stuff in the convective zone is forced to convect. Hot regions rise to the surface and cooler regions sink back down. Imagine filling up your bathtub with hot water. The water convects as the hot water moves round and round to the cooler regions, and so on and so forth. So the convective zone is where the stuff in the sun is convecting, literally. Above that is the atmosphere, in inverted commas. I use the word atmosphere here very lightly. You can't really think of it like Earth's atmosphere, for example. But the atmosphere of the sun is about 60 miles thick. The visible layer of the sun is called the photosphere. This is the bit that we can see if you were to look at the sun. Don't look at the sun, by the way, unless you have some form of protection over your eyes, because you can do your eyes irreversible damage. But this is the visible surface of the sun. It's much colder than the core. The photosphere is about 6,000 degrees Celsius. And if we look at this, one of the highest resolution images of the sun ever taken, in fact this is a little time lapse here by the Daniel K. Inouye Solar Telescope in Hawaii, we can see individual cells of the plasma, roughly the size of Texas these cells are, and they are rising to the surface through convection, as we've just learned, where they cool, darken in colour and then sink back down underneath the photosphere. So there's your photosphere. Now above that, extending away from the surface or the visible surface of the sun, we have the chromosphere and the corona. The chromosphere in this picture is that red light that you can see And I'm also actually going to break down what's going on in this picture. This is a solar eclipse, a total solar eclipse. The moon is covering the disk of the sun, the bright disk of the sun, revealing the edges of the sun's atmosphere. Chromosphere translates literally into sphere of light. And here, believe it or not, the temperature rises again from the 6,000 degrees at the photosphere to 20,000 degrees in the chromosphere, that red region where hydrogen is energized and it's glowing in that iconic red color. Now above that ghostly white looking region is called the corona, translating to crown. The corona is even hotter, about 1,000,000 degrees Celsius, or up to 1,000,000 degrees Celsius, very, very roughly. The corona consists of superheated plasma flowing along magnetic field lines. The sun, as we will see in a later lesson, has a very powerful magnetic field. Now the plasma in the sun consists of charged particles, as we've seen. Because these particles are charged, when they leave the sun through different mechanics, which we'll learn about later on, they interact with the solar magnetosphere, they follow the magnetic field lines, and they give out light. That's what we're seeing here. Superheated plasma flowing along magnetic field lines, trapped in those magnetic field lines. So there is a quick summary of the composition and the structure of the sun. I will see you later on for lesson 2.2.